Indirectly, of course, this has also an effect on climate. Yeah? And in the modern economies, I think it will be much more focus be put on circularity. Yeah? Otherwise, we will not be able to provide the necessary materials to society.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. In this episode, I'm returning to one of my favorite topics, the clean energy transition. Today, I wanted to explore the life cycle greenhouse gas footprint associated with the shift to electric vehicles. Many governments are using a transition to electrified transportation as the foundation of their greenhouse gas emissions reduction program, including Canada's. Today, I'm going to an expert to find out how effective this transition will be on our society's greenhouse gas emissions profile. If you enjoy this content, please hit like on your podcast app and please share it with your friends. If you want to chat with me, join my Facebook group, The Rational View. Dr. Gerfried Jungmeier holds a master's degree in mechanical engineering and received a PhD studying the greenhouse gas balance of bioenergy systems. He's a future energy systems researcher at Joanneum Research, now I'm going to screw up this word, Forschungsgesellschaft, MBH, in Austria. He lectures at Vienna University of Technology, Danube University Krems, and University of Applied Science Kapfenberg. He's an expert in the life cycle assessment of energy and mobility systems. Dr. Jungmeier, welcome to The Rational View.
Hello, welcome.
Could you tell me how to pronounce that research group?
My research company is called Joanneum Research Limited.
Okay, perfect. Tell me a little bit about yourself and your background, how you got to be involved in understanding electric vehicles.
Yeah, I did my PhD, as you already mentioned, on mechanical engineer. And since more than 30 years, I do environmental assessment of different things of daily life. Not only vehicles, it's also about electricity generation, building a house, having a good meal, for example, a Wiener Schnitzel or something like that, or beer or wine, a cup of coffee. So our expertise, or my expertise, is really doing environmental assessment of different products in daily life, but they're always based on life cycle assessment. That means we're really covering the whole life cycle from starting to extract raw materials in nature, making a product, using the product, and of course, on the end of life, also something happens to the product, which also makes or could make some impacts. And that is life cycle assessment. And that's the methodology we use to assess environmental effects of different products and systems.
I think this is very valuable and useful. And I think it's probably something that a lot of governments don't take into account in their greenhouse gas reductions plan. If I were to open Canada's pathway to net zero, I see a lot about building a lot of different things, and their greenhouse life cycle footprint isn't included in their budgets for greenhouse gases. You see only the emissions of the operation of these systems in their budgeting, but not the life cycle and the greenhouse gases that go into building this huge infrastructure is a significant burden on the environment. So I want to know if Canada's electric vehicle transition plan, it's been said that, we're no longer going to sell internal combustion vehicles beyond the year 2035. I want to know if this is a scientifically sound policy to reduce greenhouse gases. You've published an assessment of the life cycle carbon footprint of electric vehicles for the International Energy Agency. Can you give us an overview of your findings in this study?
Yes. Maybe I say two different things. One thing is, if you really look on the big system, it's not only a question if I use an electric car or a petrol car or even a bioethanol car. At least the question you have to start with is the demand for mobility for persons and goods. That is very often not seen. So at least we want to go somewhere, we want to buy something, goods have to be transported. So at least the starting point is really, what is the mobility service you need? What distances do you need? Why do you need mobility? You always need to go somewhere if you don't find it at the place where you are. And at least this is one aspect. And of course, there are many ways of mobility besides petrol and electric cars. You can walk, you can cycle, you can use the public transport. So one of our research, of course, is to analyze the different mobility needs of people and how to satisfy them in a at least climate-friendly, low greenhouse gas way. So this is the first part. And the second part, if you really break it down to selecting a petrol car or an electric car, of course, then it's a pure technology comparison, more or less. Yeah? And our main findings are, of course, all these assessments have to be made on a life cycle basis. That is especially important for electric vehicles, as the production of the battery has significantly higher emissions compared to a normal combustion engine vehicle. And so you have more emissions by making the battery electric vehicle. But of course, during the driving, during the operation, the electric vehicle has no stack, so no direct emissions occur. But of course, it's important, where is the electricity coming from? That is the second key question. Beside the battery, where is the electricity coming from? And at least on the end of life, it's also a question what's happening to the vehicle that is more or less solved, but also what's going to happen to the battery. And that also, in most of the cases, we expect that we are going to recover the material like for the rest of the vehicle. So it's very important to really cover the whole life cycle. And what really determines the differences between a petrol car or a diesel car and an electric battery car is the size of the battery. How big is the battery? And we have seen, as the battery is getting cheaper and more energy dense, in general, the battery is getting bigger because people want to have more driving distance, of course. But making a bigger battery, of course, makes higher emissions than making a smaller battery. And secondly, it's also a question where this battery is made. In the past, most of the batteries, they came from Asian countries. And they have been produced in smaller production plants. Now we see more and more battery factories popping up in the US, so in North America, but also in Europe. So many big gigafactories going in operation, and they're more efficient because they are bigger. And they are also less polluting because, in general, the electricity mix or the energy mix in Europe is cleaner than in the US. So it's a question of where do you produce the battery and how big is the battery. And the next thing is about the energy consumption. How much energy do you need to drive a kilometer? And normally, it's not enough just to look on the driving. I'm located here in Austria, in Graz, and we have cold winters and more hotter summers. So you also have to heat your cabin in the winter and cool it in summer. And so also this energy, especially in winter, for a conventional petrol vehicle, it's not a problem to heat your cabin. But for an electric vehicle, the energy has to come from the battery also. So at least, and if you drive a short distance with a battery electric car, maybe you spend more electricity on heating the cabin than for the driving. So you can put on the warm clothes, of course, that would help. But anyway, what I want to say is you really have to cover all the energy you need in the vehicle Yeah. Also to listen to your podcast, if you like to do in the vehicle, you need energy for that. Yeah. And that has to be included. And of course, that depends on the driving cycle and if you go up or downhill or whatever. And that has also for conventional vehicles a significant influence. And the third important thing is really, where is the electricity coming from? And what we have seen is, of course, the more renewable electricity you use, of course, the lower the emissions are. Yeah? And I know that Canada, like Austria, we all have already a high share of hydropower. So this is renewable electricity, which has, at least in a life cycle, quite low emissions, but not zero emission. Because even if you have to build a hydropower plant, you need concrete, you need steel, you need the turbine and whatever. So even that is counted for in the LCA. So you still have per kilowatt hour maybe 20 grams of greenhouse gases, compared to natural gas where it's 400. For a coal power plant, it's 800 or 900. So it's significantly lower, but it's not zero. That's also important to understand, that in life cycle assessment, at least nothing is zero. Couldn't be zero. Yeah? So if you have the hydropower in Canada, or like we have here in Austria, this is renewable electricity. But the pity is that at least all the existing renewable electricity is used already. We use it for cooking, for talking to you on the PC, for using the internet, for all that stuff. So if I start to plug in a new battery electric vehicle, I have to make sure that also additional renewable electricity is generated. Yeah. Otherwise, of course, in the electricity mix, maybe a natural gas power plant or a coal power plant provides me this additional electricity. But this is in the terms of greenhouse gas saving, not the best way. Huh? So at least it's really important that the electricity mix, at least for the electric vehicle, has a high share of renewable and is really additional renewable electricity. Yeah.
Yeah, here in Ontario, we're very lucky that we've got a 60% share of nuclear electricity on our grid. So we've got one of the cleanest grids in the world here, luckily enough. So that, I think, assuages our conscience quite a bit in terms of the source of electricity for driving electric cars, at least in Ontario. But I know other provinces like Alberta is very heavily into oil and gas, and they have a very dirty grid out there. But you're right, and Quebec has a very high hydro electricity, and British Columbia also have high hydro components. So you're saying that in places where you're powering your car from clean electricity, non-emitting sources, or low life cycle greenhouse gas sources, you're going to do better on your electric vehicle. And Canada's a very large country here, so mobility is very important. We have to drive long distances to go from place to place. So I'm sure people are going to want to have a large battery here. Canada's a cold country, colder even than Austria. Battery performance scales poorly with temperature. When it gets colder, batteries perform worse. So supposedly we would need even larger batteries just to get from place to place in Canada. Can you give us a ballpark of what sort of impact this has operating vehicles in cold climates on their efficiency?
Yes, at least in cold climate, the battery works less efficient. And of course, you need more of the electricity from the battery to heat your cabin. At least that might also reduce significantly your driving distance per charging. That means, in other words, you need to charge more often. Yeah, you need to charge more often, maybe each 200 kilometers or 250 kilometers if you make a long ride. At least that is a question if you have a fast charging station available on these long rides. Yeah? So if you drive 250 kilometers, maybe you need a break to take a coffee or something to eat. And if that takes you half an hour or so, you can at least recharge your car with a fast charging infrastructure significantly. Yeah, up to so you get another 200 kilometers maybe in this 40 minutes or 30 minutes. So at least you need to make more breaks on longer driving, which is very often the possibility also to make a break. So with that, you could also overcome longer distances by making stops. But you need a quick charging facility there, because with a slow charging, it takes you some hours to charge your car. So at least the faster the charging is, the better it is. And there's a very well-known company which establishes these fast charging stations on many highways, not at least in Austria. I don't know how it is in Canada, but this shows at least that for this premium segment, they have also established this quick charging infrastructure. And that demonstrates at least that it's also possible really to drive longer distances and have a good break in between.
Okay. I've in preparation for this interview, I looked at a lithium battery manufacturer's website, and it states that batteries are safe to use in cold temperature climates ranging from -4 degrees Fahrenheit up to 140 degrees Fahrenheit, which makes them practical for any weather conditions. But we commonly get, -40 degree weather here. Is it safe to get to work with my EV in -40 degree weather?
I would say yes. I was in Norway last week, and in Norway, which is also a very cold country, but has the highest share of electric vehicles globally, I would say. And they did also much testing under cold conditions. And I saw some videos and testing in cold climate on ice and snow. And I think at least it's safe and it works. So at least you can use it in cold climates, and it's also safe at least to use it in cold climates. Yeah.
Okay, good. That's good to know. Keeping with the focus on batteries as kind of the driving force behind these things, are there ethical concerns with the mining of lithium for EV batteries if we're going to have a huge burst in the EV market due to the energy transition? Is this going to affect third world countries? Because I know a lot of the lithium mining happens in third world countries under questionable environmental conditions. Do you have concerns with that?
Maybe a side remark. We have also a significant lithium resource in Austria, and we're currently discussing of exploring it because that is mainly due to the increasing demand of lithium globally. Of course, more and more new resources are discovered because the demand, and I think that's the first part of my answer, is that if we have more battery electric cars, we need much more of these materials like cobalt, nickel, copper, and lithium, of course. Yeah. And so at least the supply of these raw materials has to significantly increase. Yeah. And this is one thing which is economically, I'm not an expert on economics, but I think it could work. And it showed in the past that this ramping up of this quick introduction, I think we have more than 20 million battery electric vehicles globally, which ramped up in the last few years. So it was possible to supply these amounts of materials to maybe also a reasonable price, however. But of course, there are some social or ethical concerns for some countries. If it's cobalt or if it's nickel or it's lithium, yes, there are some concerns. I'm not an expert on the details on that, but I'm aware there are some critical aspects that have, of course, to be guaranteed that the battery will be produced under fair conditions, which is at least, to be honest, not only a question of the battery production. It's a question of all the products we have in daily life. If you buy a cheap T-shirt produced in Asia, there's also discussion about that. So at least it's a general question for everything that we need fair and fair conditions, social fair conditions. But of course, and that also covers, of course, lithium and cobalt and maybe also nickel. And that has to be at least guaranteed via different supply chain declarations, or how you call that. Yeah.
Yeah. So getting down to nuts and bolts here, overall, the electric vehicles are more energy efficient than internal combustion engine vehicles because all the energy in the battery goes directly to motion, whereas in an internal combustion engine, 2/3 of the energy is lost to heat. And if you're not using that heat in the summer, at least it's wasted. In the wintertime, it becomes a closer comparison because some of the battery energy needs to be used to make heat, as you said. The EVs, however, carry much more mass due to their heavy battery compartments. So on an energy per unit distance metric, how do they stack up? What's the balance? Can you give us like a percentage? How much more efficient is the electric vehicle?
Yeah. So, of course, the size of the vehicle is a question, and the bigger the vehicle, the more energy you need. Anyway, for a big electric vehicle, you have the possibility by braking to recover a certain share of the electricity that you don't have with a combustion engine. And if you drive downhill only, maybe you can recharge your battery. However, this is one aspect. And when we talk about energy efficiency, there are also two things that have to be considered. One is the pure efficiency of the vehicle. So petrol going in and the driving, or electricity charged and driving. So this is only the vehicle. And normally for a battery electric vehicle, you use maybe 20 to 25 kilowatt hours per 100 kilometer. So 20, 25. If you convert that into a petrol car, I would say you need 50 to 70 kilowatt hours of petrol per 100 kilometers driven. Yeah? So it's more than double of energy. In one case, it's electric energy. In the other way, it's the heating value of the petrol. This is the one part of the vehicle. In the overall energy efficiency, that has to be judged again based on life cycle assessment. And life cycle assessment has an indicator saying how much primary energy do you have to take from nature to drive your vehicle. And at least if you do that from the raw oil to the petrol station, you need maybe additionally 10 to 50% of the energy in the petrol to bring it from the raw oil with the refinery and all the transportation to the vehicle. So you have to add maybe 50 to 20% additional energy to bring it from the raw oil to the petrol station. For the battery electric vehicle, it depends on how you make your electricity. If you make it in a thermal power plant like nuclear, coal, or natural gas, the efficiency is you need 2 or 3 units of energy to make 1 unit of electricity. Yeah? So in that case, especially with thermal power plants, you eat up at least the efficiency gain in the vehicle, you eat up with the efficiency losses of the thermal electricity generation. Yeah? So and on that, it's maybe the same amount of primary energy you need to drive 100 kilometers. If you go to renewable electricity, like wind, photovoltaic, hydropower, of course, the efficiency conversion of wind and water into electricity, it's much more efficient. Yeah? So you mainly have some grid losses of maybe 4, 5, or 6%, however. So at least, again, if you have renewable electricity, also the overall primary energy efficiency is on the first double efficiency compared to a petrol or a diesel car. Yeah? As soon as you start to involve also thermal power from nuclear, from coal or natural gas, the energy efficiency is maybe a little bit in advantage of battery electric car, but not so significant. Yeah.
So I just wanted to provide a little commentary to help you understand a little bit more about what Dr. Jungmeier is talking about when he's mentioning efficiency and the efficiency of thermal generators versus the efficiency of so-called renewable generators. So renewable generators are sources that go directly from the source to electricity without using a thermal component. So you have solar panels that take photons and turn them into electricity. You have windmills that turn turbines that make electricity, and you have hydro, which has water pressure that creates electricity. Thermal generators create heat that turns a turbine that makes electricity, and in this process, some heat is lost. So the efficiency of the primary to electrical transition is about a factor of 3 lower in a thermal generator. Now, thermal generators include coal, they include gas, they include nuclear. So when you're looking at the efficiency of an electric vehicle in terms of 20 to 25 kilowatt hours per 100 kilometers, that's electrical efficiency. And if you look, and the reason that's better than a internal combustion engine is because you have the penalty of changing heat energy into motion. And that's that inefficiency of a thermal generator. It's a factor of 3 penalty on any thermal generator. And so it increases the overall greenhouse gas footprint of thermal generation sources like coal, gas, and nuclear. But if you want to look at the greenhouse gas footprint of these things, you have to look at also the intensity, the greenhouse gas intensity of the emission source. So, and this includes the greenhouse gas that contribution for manufacturing the power source and for mining the fuel or mining the raw materials and for decommissioning at the end of life and storing or recycling the waste at the end of life. So all of these things have been done, and the IPCC has stated back in 2014 that wind and nuclear are about 12 grams of CO2 per kilowatt hour. Okay, so very similar. The thermal penalty isn't hurting nuclear much there at all. In fact, it's on the same footing as the so-called renewable generator. And then solar panels are much higher. They're about 43 to 50 grams of CO2 per kilowatt hour. Gas emits about 400 grams CO2 per kilowatt hour. And I had mentioned the fact that leakage of methane from fracking just about doubles that, makes about 800 grams of CO2 per kilowatt hour. And then coal is about 900 grams of CO2 per kilowatt hour. So huge orders of magnitude here. But looking at the clean sources like wind, solar, nuclear, and hydro, they're all clustered about an order of magnitude lower than coal and gas. And nuclear is about an order of magnitude lower than solar because solar is such a low density material that you need to manufacture quite a bit of stuff using high temperature processes to make these solar cells. And the other factor that's not included in this analysis is the impact of intermittent sources on the backup system of the electrical grid. Most electrical grids that don't have hydro or don't have a lot of hydro or don't have a lot of nuclear are relying on gas peaker plants to back up their renewable, intermittent weather-dependent sources like wind and solar. And these things are more inefficient than typical baseload gas plants because they have to throttle back and forth and up and down. So they're not thermally efficient. They can't keep the temperature up. They have to throttle up. It's like on-demand hot water. It's just not as efficient as a insulated source that's always running. And so what you look at is the actual greenhouse gas impact of having a renewable-based system versus a hydro or nuclear-based system where you have a dispatchable energy source. And that really creates a bit of a penalty to your electrical grid and to your greenhouse gas sources. So the actual footprint of a grid that doesn't have nuclear or hydro in it can be quite high. But Austria is graced with good hydroelectric resources, so it's going to have a very low greenhouse gas footprint. Quebec and British Columbia also have lots of hydro, so they have good baseload, clean baseload from hydro. The prairies in Canada, however, are mainly coal and gas, coal and oil and gas. And these are going to have not as significant a benefit for powering your electric vehicle until they switch to a cleaner baseload. Okay. So, yeah, changing thermal primary energy to electricity gives you a penalty and efficiency of something like 35%, depending on the power plant. Obviously, uh, thermal electricity from an industrial power plant transmitting to energy is more efficient than thermal energy in a small engine, right? There's some advantage to going to to an industrial source, even if you are still using polluting energy like gas or something like that. There is some advantage to using an EV in a dirty grid in terms of efficiency. Is that correct?
Yeah, that's correct. And maybe if we're talking about cold countries like Canada, of course, if you have a thermal power plant running in wintertime and you make the electricity maybe for the electric vehicles and you use the heat with district heating for heating a town, or a city or a village, of course, then you get more. This combination in cold countries is quite in favor. Like we have in Austria, the big cities, they all have CHP, combined heat and power plants, running during winter time. Also heating, my apartment is heated by natural gas, but in a combined heat and power plant. So in that way, it's still quite efficient if you can use the heat.
Yeah. I don't know if that's done very much in Canada, but it certainly should be looked at. It's a significant advantage, and anything that don't waste your heat if you've got it. It definitely should be used. So overall, 20 to 25 kilowatt hours per 100 kilometers for an electric vehicle is the rough range. 50 to 70 kilowatt hours per 100 kilometers for a gas vehicle. So effectively a factor of 2. And this takes into account some comparison in the mass disadvantage for the batteries, correct?
Yes. It's at least made for similar vehicles.
Yeah. Okay. And then you're also saying that you have to take into account your power source. So an electric vehicle in a grid with low greenhouse gas emissions intensity is a much better purchase than an electric vehicle in a dirty grid.
Yes.
Mm-hmm. Mm-hmm. Because effectively you're not necessarily getting clean electricity. You're getting as a coal grid, it's 900 grams per kilowatt hour, and gas, it's 400 grams per kilowatt hour plus methane emissions, which could bring it up to 900 grams if it's 3% emissions.
Yeah. It's that's also important that on the greenhouse gases, we not only count for the CO2, we also have to count for the methane. It's relevant for coal, but also for biogas or natural gas, and also the N2O, which is relevant if you have some biofuels involved. I think also in Canada, you have a little bit ethanol blended in the petrol. So it's always relevant to have all the greenhouse gases in that comparison to really have a reasonable matrix.
Mm-hmm. So looking at the whole stack up, for someone who has an existing internal combustion engine vehicle, what is the most environmental choice for Canada? Are we should one switch immediately to their EV? Should they sell off their internal combustion engine vehicle, or would owners, because of the impact of the manufacturing energy already in that internal combustion engine vehicle, all the products that have been put into that and the manufacturing that has gone into it, and the greenhouse gas footprint that has already been swallowed, what fraction of the footprint of a vehicle is in the manufacturing versus the operating and would it be a better idea to continue running the internal combustion engine vehicle until it gets old and then switch, or should we switch immediately? What's the best option for the environment?
Let me again bring that question first to a more general level. It's at least also a question, how often do you use your car? How fast do you drive? And do you take somebody with you, or do you drive alone? Yeah. So, and this is at least to mention that it's only one question is the technology, and the other half is really your behavior. And in my research group, we are dealing with future energy systems and lifestyle, because we know that in future climate-friendly lifestyles, you need to change your lifestyle, and you need better, more efficient technologies. But we need both. Yeah. So if you have a petrol or diesel car which is 2 or 3 years old, your first step would be to maybe reconsider your driving behavior. If you drive slower, and maybe you combine different travels, yeah, and that maybe saves more greenhouse gases immediately, yeah. And then when your engine is getting older, of course, it makes sense, because for a petrol car, the contribution from the car making is in the whole life cycle on greenhouse gases 50 to 20%. Even less, I would say 10 to 50% is coming from the vehicle production, because the combustion of the petrol and diesel, that is the heavy CO2 emission during operation. For the battery electric vehicle, it's the other way around. If you use renewable electricity from hydropower, this is maybe only 10% of the overall emissions, and 90% is coming from the vehicle production in a percentage way, but still on the absolute values, you're still significantly below a petrol car. But in general, so as a first thing, when you buy a car at the dealer, maybe an average car has 7 tons of CO2, petrol or diesel car. If you have a battery car, it's 12 to 15 tons. Yeah, just to get a feeling. So it's not a full factor 2, but maybe 40% more emissions when you buy it at the dealer. But then if you use renewable electricity during operation, you eat it up, you save roughly 2 tons per year. Yeah. So maybe after 2 or 3 years, depending on how much you drive, you have more or less so-called break-even reached, yeah, to compensate for this higher emission. And at least, but you need really renewable electricity. Otherwise, it does not work that way. Then it takes longer. So at least to answer your question, finally, reconsider your mobility behavior, yeah, and then think on other technologies, yeah, including also walking, cycling, and public transport, which is an old story, but in terms of greenhouse gases and energy efficiency, it's quite efficient. Yeah.
Yeah, that's something that we fall down on a lot in North America with our large spaces and long distances. It's designed for a driving economy. Unfortunately, much of our infrastructure is separated, and in our climate, walking is sometimes not even available as an option.
Yeah. I know. Yeah.
But in terms of the trade-off, you're saying it's less than a factor of 2 in the initial greenhouse gas, and then the operating of the internal combustion engine is going to be something like on the order of 2 tons a year of additional greenhouse gas emissions that you're adding to it. So in
maybe
5
in
years,
Canada, it's up to 3 tons, because you're a bigger country and drive maybe more than in Austria. So maybe it's 3 ton. Yeah.
Mm-hmm. So basically, driving an internal combustion engine vehicle for 3 years, you're emitting as much as it would cost to build a new electric vehicle.
Yeah.
So that's the sort of trade-offs that we should be considering in terms of how much we can save. So, it's additional manufacturing to build these new electric vehicles, but after 3 years of driving them with a low emissions electricity system like nuclear or renewable or hydro, we're going to be getting that back. And so it's really excellent in terms of the environment to make this decision, even in a cold country like Canada. Although it's not as good as in a warm country where you don't have to worry about these cold things, it still makes environmental sense to switch early. I think that's the message that you're providing here.
Yeah.
In terms of the overall greenhouse gas advantages associated with this transition, though, I think you would advocate that the life cycle impacts need to be accounted for in any sort of budget. So we should be telling our governments to make sure that you're looking at the life cycle budgets of these things when you're adding up your greenhouse gas savings. If you're going to manufacture all of this stuff, you need to make sure that you're doing it right. I think that's part of the rational view of this transition, is to look at the greenhouse gas impact and look, as you mentioned, at the end of life recycling as well. Because if this is just going to the junkyard at the end of life and the material isn't coming back, that's a significant impact on the greenhouse gas footprint, isn't it?
Yeah, maybe not on the greenhouse gas footprint. If you just dig it in your garden, that's maybe not relevant for greenhouse gases, but you lose all the raw materials. Yeah, the lithium, the cobalt, the nickel, the copper, the aluminum, and the steel. So at least you really have to get these materials back. And this circularity issue is mainly relevant for the end of life. It's maybe not so much the greenhouse gas, but the greenhouse gas effect is a secondary effect, because if you can recover secondary material, you avoid producing primary material. So if you recover the steel or the lithium, you don't have to make fresher primary material. So indirectly, of course, this has also an effect on climate. Yeah. And in the modern economies, I think it will be much more focus be put on circularity. Yeah. Otherwise, we will not be able to provide the necessary materials to society.
Yeah. Okay. So this has been a very helpful discussion. I really appreciate your insights and you coming on the show and giving us these insights in terms of your work on electric vehicles and greenhouse gas life cycle. So thank you so much for coming and joining us. For coming on the show, I'm going to send you a T-shirt for the Rational View.
Yes.
Really appreciate your time coming to chat with us. And one quick word in closing, one question. Do you enjoy science fiction at all? Do you read science fiction, or do you have any favorites?
No, not at all. No, not at all. No.
Okay. Rated a reality person.
Maybe, yes. No.
Okay. So thank you very much for coming on the show. I appreciate it.
It was a real pleasure to meet you. Thank you very much for inviting me.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/TheRationalView. Thanks for listening.